Everyone often imagines that somewhere out there are advanced civilizations looking toward us, or even that they have already visited Earth. But let's pause for a moment and think about this carefully, because in 1950, Enrico Fermi posed a question at Los Alamos: where is everybody? And that question becomes far more thought-provoking when you look at the actual numbers. The universe may contain about 2 trillion galaxies, each with hundreds of billions of stars. Our own Milky Way alone has roughly 100 to 400 billion stars, and many of them have planets. If even a small fraction of those have suitable conditions, then over the 13.8 billion year history of the universe, intelligent life could have emerged many times. Yet when you return to reality, we see no signs whatsoever. No spacecraft, no clear radio signals, no massive structures like Dyson spheres. And that's when you realize that the silence of the universe is not a science fiction story, but a real physical problem that needs to be explained. Now let's look at the real issue, because the nearest star to us, Proxima Centauri, is about 4.24 light years away from Earth. That's nearly 40 trillion kilometers, and that's just our closest neighbor in the universe. Light, the fastest thing we know, travels at approximately 299,792 kilometers per second, a figure that has been measured with extreme precision since the 20th century. And according to Albert Einstein's 1905 theory of special relativity, no object with mass can reach or exceed that speed, not because we aren't smart enough, but because the universe simply doesn't allow it. Now suppose you want to reach Proxima Centauri in a reasonable amount of time, say 50 years. You would need to travel at about 10% the speed of light, which is roughly 30,000 kilometers per second. That number is thousands of times faster than the fastest spacecraft we have ever built. The Parker Solar Probe only reaches about 200 kilometers per second. And things get even worse when you expand your view to the entire Milky Way, which has a diameter of about 100,000 light years. Because even if you could sustain 10% of the speed of light, crossing the galaxy would still take about 1 million years, a period far longer than the entire history of modern humans, which is only about 300,000 years. So the question is no longer whether we can build a ship, but whether any civilization, no matter how advanced, would truly be willing to commit the resources, time, and stability required for a journey that vastly exceeds the lifespan of the civilization itself. And that's when you begin to realize that distance and the speed of light are not just technical difficulties, but the first and greatest barrier written directly into the structure of the universe. And if you think that solving the speed problem would make everything fine, this is where all ordinary intuition completely collapses. Because when an object approaches the speed of light, the effects of special relativity stop being abstract theory on paper and become precisely measured real-world phenomena. One of the most important effects is time dilation. Time no longer flows the same way for all frames of reference. This has been proven by experiments with atomic clocks flown on jet planes since the 1970s, as well as in modern particle accelerators, where particles traveling near the speed of light have much longer lifetimes than when they are at rest. Now imagine you are on a ship traveling at 99% the speed of light. For you, the journey might last only a few years, but on Earth, decades or even centuries could have passed. And that means when you return, you are not coming back home anymore. You are returning to a future you no longer belong to. The entire social context, language, technology, and even the people you once knew could have disappeared, and you become someone displaced from the timeline of your own civilization. But it doesn't stop there, because according to Albert Einstein's equations, as your speed increases, your relativistic mass also increases. This means that every time you try to accelerate a little more, you need far more energy than before. Not linearly, but in a way that quickly spirals out of control. At some point, the amount of energy required to continue accelerating becomes enormous, and as you approach the speed of light, the required energy approaches infinity. That means you can get as close as you want, but you will never actually reach that limit. The important point here is that this is not a problem of us not having enough technology or not being smart enough to solve it. It is a barrier written directly into the mathematical structure of the universe, a limit that any civilization, no matter how advanced, must face. And when you truly understand this, you begin to realize that interstellar travel is not just a difficult technical challenge, but a problem that the laws of physics themselves seem designed to prevent you from solving. And if all of that still isn't enough to make you feel that something is wrong, we need to step back and look at an even more fundamental problem: the way you understand distance in the first place. Because your brain was not designed to understand the universe. It was designed to survive on a small planet with distances of just a few kilometers or a few dozen kilometers, distances you can travel in a single day, spaces you can observe with your own eyes without needing too much imagination. When you think about distance, you think in terms of lived experience. You think in terms of roads, cities, and countries, but you have no experience to attach to numbers like trillions of kilometers. And that is where everything starts to break down, because a light year is not a unit of time, as many people mistakenly believe. It is a unit of distance, equivalent to about 9.46 trillion kilometers, a number so large that if you try to visualize it, you don't actually see anything in your mind. You're just repeating a meaningless string of digits. The problem here is not that you aren't smart. It's that you weren't designed to comprehend these scales. And that leads to a very dangerous mistake. You think you understand the universe just because you know its numbers. But let's try a different, very simple approach that requires no complex math, just a comparison. Suppose you get in a car and drive at 100 kilometers per hour, a completely familiar speed, without stopping, without resting, without accidents, without maintenance. You just keep going forever. Your destination is the nearest star, 4.24 light years away. You would take more than 40 million years to get there. Not 40 years, not 40,000 years, but 40 million years, a period longer than the entire history of modern humans, longer than the time since our ancestors first began using stone tools. At this point, the issue is no longer technical. It is perceptual, because your intuition completely fails. It has no tools to process numbers like that, and therefore it constantly underestimates how difficult the problem actually is. You may think that reaching 10% of the speed of light is an ambitious but achievable goal. You may think that a few decades is a long journey but still acceptable. But all of those thoughts are built on a false foundation. You are applying the experience of a creature living in a small world to a universe that is almost infinitely vast. And things become even clearer when you break the number down in another way. If you flew in a commercial airplane at about 900 kilometers per hour, you would need more than 5 million years to reach the nearest star. And if you use the fastest spacecraft we have ever built, like the Parker Solar Probe at about 200 kilometers per second, you would still need thousands of years to complete that journey. These are numbers that no longer fall within the experiential range of any civilization. What is even more important is that when you expand your view beyond the nearest star system and look at the entire Milky Way, you are talking about distances of up to 100,000 light years. And even if you could maintain 10% of the speed of light, crossing the galaxy would still take about 1 million years, a period far longer than the lifespan of any civilization we have ever known. And this is the key point. Our first and greatest mistake is misjudging the scale. We think this is just a big problem, but in reality it is so large that it completely collapses the way we think about space, time, and motion. Science does not make these numbers easier to understand, to fit your intuition. It forces you to abandon that intuition and accept the reality where the numbers no longer relate to everyday experience. And when you truly understand this, you begin to realize that the problem is not that we don't have the right technology, but that we started from a wrong assumption right from the beginning. That distances in the universe are something we can cross the same way we cross distances on Earth, when in reality, those distances exist on an entirely different level. a level where simply understanding them is already a challenge, let alone conquering them. Once you have begun to realize that the scale of the universe has completely surpassed your intuition, the next step is even harder to accept, because even if you can imagine some way to overcome those enormous distances, you are still blocked by a limit that no one can negotiate and no one can break: the speed of light. The important thing to understand is that the speed of light is not just a large number of about 299,792 kilometers per second. It is a fundamental constant of nature. It has the same value in every frame of reference, no matter how fast you are moving or from where you are observing. And it was precisely this that forced Albert Einstein in 1905 to completely rebuild the way we understand space and time. The consequence is that space and time are no longer independent, but are joined together into a single structure. And within that structure, the speed of light acts as an absolute limit, a ceiling that no object with mass can exceed. And this is where many people make a mistake. They think that with enough technological progress, an advanced civilization could find a way to go faster than light. But that is intuitive thinking, similar to believing that if you build a strong enough airplane, it will eventually fly faster than anything, when in reality, you are trying to break a law that was not made by humans. To see this clearly, look at what we have actually done in practice. In particle accelerators like the Large Hadron Collider at CERN, we have accelerated protons to more than 99.9999999% of the speed of light, meaning they come extremely close to that limit, but never surpass it. What is interesting is that when you continue to pump more energy into the system, the speed of the particles only increases by an extremely tiny, almost negligible amount, while the energy you must supply increases very rapidly. And this is not a technical problem, but a property of the relativity equations. As speed approaches the speed of light, the energy required to accelerate further approaches infinity. And infinity here is not exaggeration. It is the exact mathematical result. It means you can get as close as you like, but you will never reach it, just like you can approach the horizon but never set foot on it. This leads to a very important consequence that is often overlooked. Every civilization, no matter how advanced, if it exists in this same physical universe, must face the same limit. They do not have a better version of physics. They do not have their own laws. They cannot negotiate with the constants of nature. You can imagine they have technology millions of years ahead of us, but that does not change the fact that they are still bound by the same equations, the same speed limit, and the same space-time structure. And this completely changes the way you look at the problem of interstellar travel, because it is no longer the question, when will we be smart enough to do it? But rather, is this even within the realm of what is possible? And when you look at all the experimental evidence, from laboratory experiments to modern particle accelerators, the answer gradually becomes clear. It is not that we have not yet reached the required level, but that the universe itself has set a limit that no one can surpass. And once you accept that, you begin to understand that the speed of light is not just a number in a textbook. It is an invisible wall, an absolute barrier, and that very barrier is one of the strongest reasons why the universe, even if it may be full of life, remains completely silent. Once you accept that the speed of light is an insurmountable limit, the next thing you are forced to confront is an even more practical and brutal problem: energy. Because even if you are not trying to reach the speed of light, but only aiming for a more modest figure like 10% of the speed of light, you still have to pay a price that is almost unimaginable. Let's take a concrete example. A spacecraft with a mass of about 1,000 tons, that is 1 million kilograms, and you want to accelerate it to 10% of the speed of light, or about 30,000 kilometers per second. If you apply the relativistic kinetic energy formula, you get an energy figure of approximately 4.5 × 1020 joules, and this is only the minimum estimate under ideal conditions. Now put that number into context. All of humanity today consumes about 600 exajoules per year, or 6 × 1020 joules. That means that just to accelerate a single ship to 10% of the speed of light, you would need nearly all the energy that the entire human civilization uses in a whole year. And that assumes you could focus all that energy on a single task without any losses, which is impossible in reality. What is more important is that this is only the initial acceleration phase. You have not yet traveled. You have not faced the space environment. You have not solved the biological problems, and especially you have not accounted for stopping. Because when you reach your destination, you cannot just fly through that star system at 30,000 kilometers per second. You have to decelerate. And to do that, you need an equivalent amount of energy as you did for acceleration, meaning you have just doubled your energy problem. If you want to return, you have to repeat the entire process again, multiplying the total energy requirement many times over. And none of these numbers have even factored in the efficiency of the propulsion system, energy losses, or the mass of the fuel that must be carried, factors that will make everything exponentially worse. This is where you begin to see clearly that the problem is no longer we don't have enough technology, but we are talking about energy levels on the scale of a planet, or even a Type 1 civilization on the Kardashev scale. You can imagine an even more advanced civilization that can harness the energy of an entire star. But even then, the question remains, would they be willing to expend a significant portion of their resources just to send a ship to another star, especially when the outcome of that journey brings no direct benefit? And this is the key point. Energy is not just a technical difficulty. It is an economic barrier, a strategic barrier, a real-world barrier. Because any civilization must optimize how it uses its energy. And interstellar travel, when you look at the real numbers, is one of the most inefficient uses of energy you can imagine. This leads to a very uncomfortable but extremely clear conclusion. It is not that no one is smart enough to achieve interstellar travel, but that its energy cost is so enormous that even an advanced civilization might decide it is simply not worth doing. And when you combine that with the speed of light limit we discussed earlier, you begin to see a consistent picture. The universe does not need to stop you actively. It only needs to set the numbers large enough and harsh enough that anyone who tries to overcome them must stop and ask themselves whether it is truly feasible. When you begin to solve the energy problem in theory, another issue immediately appears, and this time it is not only physics, but also your own experience, time. Because when a ship travels near the speed of light, the phenomenon of time dilation is no longer a minor detail, but becomes central to the entire journey. This means that time on your ship will pass more slowly compared to Earth. And this difference is not small. It can be extremely large as you approach that limit. Imagine a ship traveling at 99% the speed of light. For the people on board, the journey might last only a few years, perhaps 5 years or 10 years, a length of time that humans can accept. But on Earth, that same period could correspond to decades or even centuries having passed. And this is not speculation. It is a direct consequence of the relativity equations that have been verified. This leads to a very profound consequence that many people do not think about when talking about interstellar travel. You are not only leaving your planet, but also leaving the timeline of your own civilization. When you return, if you can return, you will not be coming back home in the sense that you understand, because all the people you knew, family, friends, and personal relationships will have disappeared. Not because you were gone too long according to your own perception, but because the outside world has moved far ahead. Think about the difference between the year 1000 and the year 2000. That is a span of 1,000 years. In that time, humanity went from feudal society to the industrial age, and then to the digital era. Language changed, technology changed, and the way humans think and organize society changed completely. And if you jump across such a time span after a journey that for you lasted only a few years, you will become a stranger in your own civilization. This is not only an emotional problem, but also a structural one, because every plan and every goal of the journey is based on a specific society. And when that society no longer exists in the way you knew it, the meaning of the journey is also destroyed. That leads to a very uncomfortable question you are forced to face. Whether a journey in which you know in advance that you will never return to the same era, the same society, or the same people who sent you is truly a journey you want to undertake. And this question applies not only to individuals, but to an entire civilization. Because if you invest enormous resources to send a ship, but the results of that journey can only be observed by a distant future society that you cannot predict, then the motivation to do it becomes very faint. This is where time shifts from a physical variable to a social and psychological barrier, because it breaks the continuity between cause and effect, between sender and receiver, between goal and meaning. And when you combine this with all the previous problems of energy, speed and distance, you begin to see that interstellar travel is not just a difficult problem, but a problem in which every solution causes you to lose an important part of the reason for doing it in the first place. And that is why time, something that seems abstract, becomes one of the strongest barriers keeping civilizations isolated in the universe. Once you have accepted that time can separate you from your own civilization, the picture expands in an even more frightening way when you look at the real scale of the galaxy we live in. Because the Milky Way is not a compact space you can imagine like a map. It has a diameter of about 100,000 light years and contains 100 to 400 billion stars. That means even if you pick a random target, it is highly likely to still be at an enormous distance that would take you tens of thousands of light years to reach. Now go back to the optimistic assumption we used earlier, that you could achieve a speed of about 10% the speed of light, a figure that is itself extremely difficult to reach. But even at that speed, if you wanted to go from one end of the galaxy to the other, you would need about 1 million years. And this is not a vague estimate, but a direct calculation from distance and speed. To put this number into context, human agricultural civilization only appeared about 10,000 years ago. That means the entire history we call civilization is only 1% of the time needed to complete a journey across the galaxy. And if you look further, modern humans, Homo sapiens, have only existed for about 300,000 years. That means such a journey would last longer than the entire time that humans have existed. This leads to a problem that you cannot solve with technology, the continuity of society. Because no political, economic, or cultural system we have ever known can maintain stability for hundreds of thousands of years, let alone millions of years. Empires collapse in a few centuries, civilizations change in a few thousand years, and even the most basic ideas transform over time. So you have to ask yourself, who will start a project that lasts 1 million years, and who will finish it? When those two groups are not only separated by generations, but may belong to two completely different civilizations. And the problem is not only maintaining the technology or the ship, but maintaining the goal, because the goal of a civilization is not something unchanging. It changes according to needs, circumstances, and the crises they face. And an interstellar project requires a level of stability and consistency that we have never seen in history. You can imagine an automated system, a ship that operates by itself for millions of years. But even if you solve that technical problem, the question remains, will anyone still care about the result of that journey when it is completed? And this is where you begin to see clearly that the scale of the galaxy is not just a large number, but a factor that completely destroys the idea of travel, because it stretches time to the point where it goes beyond every frame of reference we have. It breaks the connection between action and result, between cause and goal. And when you put all of these things together, distance, speed, energy, time, and now the scale of the galaxy, you begin to realize that the problem is not that we are not advanced enough to travel between the stars, but that the galaxy itself is structured in a way that makes it a nearly unsolvable task. Not because of a single barrier, but because of the combination of many barriers, each one enough to make you stop. And when they stack on top of each other, they form a system of limits that any civilization must face. Another problem that is often underestimated, but actually lies at the center of the entire space travel equation, is the way you accelerate a ship in the first place. Because in the real world, you cannot simply turn on a ship and achieve the desired velocity. You have to carry fuel to create thrust. And this is described very accurately by the Tsiolkovsky rocket equation developed by Konstantin Tsiolkovsky at the beginning of the 20th century, a deceptively simple equation with extremely profound consequences. This equation states that to achieve a certain velocity, the ratio between the initial mass of the ship and the mass after all the fuel is burned must increase exponentially. That means if you want to go a little faster, you do not just need a little more fuel, you need a lot more fuel. This leads to a strange paradox. You need fuel to accelerate the ship, but you also need fuel to accelerate that fuel itself. And that fuel in turn needs more fuel to be accelerated, creating a nested chain of dependencies. When you start applying this to interstellar velocities, the problem quickly spirals out of control. Because to reach about 10% the speed of light, even with optimistic assumptions about engine efficiency, the amount of fuel required would be so large that the ship would have to be made almost entirely of fuel, while the actual payload, where you put humans, scientific equipment, or anything of value, becomes extremely small. In some calculations, the mass ratio can reach thousands or even millions of times. That means to deliver 1 ton of payload to that velocity, you might need thousands of tons of fuel. And that is without even counting the fuel needed to decelerate when you arrive. This creates an inescapable loop, because every solution you propose to increase velocity makes the fuel problem worse, not better. You may think of more advanced forms of fuel such as antimatter or nuclear fusion, and it is true that they have much higher energy density than chemical fuel. But the basic equation does not change. You still have to carry mass to create thrust, and that mass still has to be accelerated. This leads to a conclusion that many people do not want to accept. Rocket design as we currently understand it does not scale well to interstellar distances. It works for missions within the solar system, where the required velocities are much lower, but when you try to push it to the limit, it begins to collapse under its own logic. And this is not a shortcoming in engineering or a problem you can solve by designing it better. It is a direct consequence of basic physics, something that has been understood for more than a century. So when you look at this equation, you are not just looking at a formula. You are looking at a structural limit of space travel, a limit that says every time you try to go faster, the price you have to pay increases so rapidly that it eventually exceeds anything realistic. And that is why when you apply the interstellar travel problem to this equation, it does not just become difficult, it becomes nearly impossible to carry out in the way we are imagining. And many people often overlook, when talking about just keep accelerating, that the very concept of mass no longer remains constant once you enter the region of extremely high velocities. Because according to Albert Einstein's equations, when an object moves faster, especially as it approaches the speed of light, its so-called relativistic mass begins to increase. And this is not a small effect, but a change that can become extreme. You may think you are simply accelerating a ship with a mass of a few hundred or a few thousand tons, but as velocity increases, the effective mass of that ship in the physical equations becomes larger. And that means you need more force and more energy to achieve the same rate of acceleration as before. The direct consequence is that the acceleration process is no longer a simple straight line, but becomes an increasingly steep curve, where each step forward requires far greater effort than the previous one. When you reach velocities like 90% or 99% the speed of light, most of the energy you supply is no longer used to increase speed in the intuitive way, but is consumed in increasing the relativistic mass, making it extremely expensive to move even a little closer to the limit. This leads to a very important conclusion that is often misunderstood. It is not that you should not reach the speed of light, but that you cannot reach it, because to do so you would need an infinite amount of energy. And infinite here is not a philosophical statement, but the precise mathematical result of the equations that describe the structure of space-time. You can keep adding energy and keep pushing your ship faster, but each time you do, the reward you receive gets smaller and smaller, like trying to divide a straight line into two equal parts repeatedly. You can get as close as you want to the end point, but you will never touch it. This creates a very clear boundary in physics, a boundary not set by technology, but dictated by the very nature of the universe, and any civilization that exists in this universe must face that same boundary. You can imagine civilizations millions of years old, with technology far beyond what we can imagine. But if they still obey the same laws of physics, they are also bound by the same limit. They may get closer to the speed of light than we can, more efficiently than we can, but they cannot break it. This completely changes the way you look at the problem of interstellar travel, because it eliminates the idea that if we are just advanced enough, we will be able to do it. Instead, it places an absolute limit that no level of progress can overcome. And when you combine this with the rocket equations, with the energy problem, with the scale of the galaxy, you begin to see that these barriers do not exist in isolations, but reinforce one another, forming a tightly constrained system of limits, where every attempt to overcome one barrier is blocked by another. Therefore, the conclusion is no longer speculations, but a logical consequence. It is not that we are not developed enough to reach the stars, but that the mathematical structure of the universe itself defines a limit that no civilization can break. And that is why the idea of moving freely between star systems, no matter how appealing, may lie outside the realm of what can actually happen. What many people often imagine incorrectly about space is that they think it is completely empty, a clean void, where you can move at extremely high speeds without obstacles. But the reality is completely different, because the space between the stars is still filled with dust particles, atoms, and tiny micrometeoroids that you can barely see. At low speeds, they are insignificant. But when you start talking about relativistic speeds, everything changes completely. Imagine a ship traveling at about 0.5 times the speed of light. That is about 150,000 kilometers per second. At that speed, even a dust particle with a mass of only a few milligrams carries an enormous amount of kinetic energy. And upon impact, the energy released can be equivalent to a large explosion. In some estimates, it can even compare to the energy of military explosives or higher, because kinetic energy increases with the square of the velocity. This means you do not need a large rock to cause danger. A tiny particle is enough to cause serious damage. And when you travel through space for years or decades, or even thousands of years, the probability of encountering such particles is no longer near zero, but becomes almost certain. The problem here is not just a single collision, but millions of small collisions accumulating over time. Each collision takes away a piece of the ship's structure, weakens the protective hull, and eventually leads to system failure. To deal with this, you need an extremely complex protection system, perhaps thick shielding layers, powerful magnetic fields, or systems to detect and destroy objects ahead. But every such solution carries its own cost. It increases mass, increases the required energy, and makes the problems we discussed earlier even worse. And even if you design a theoretically perfect system, you still have to face the reality that you are moving through an environment that is not completely predictable, where larger, faster, or simply undetectable objects may exist. This creates a risk that cannot be completely eliminated, a probability of failure that you must accept if you want to undertake the journey. And when you combine that with journey times lasting dozens or hundreds of years, or even thousands of years, the accumulated probability of a catastrophic event becomes very high. This is no longer a purely technical problem, but a statistical one, where you are betting that throughout the entire journey, there will not be a single collision large enough to destroy the ship. And that is an extremely risky bet. So when you look at the overall picture, space is not an open road, but an environment full of hidden dangers. And when you travel at extremely high speeds, those dangers are amplified to the point where even a small mistake is enough to end the entire missions. And that is why collisions, a factor that seems minor, become one of the most serious barriers to any interstellar travel effort. Another problem that is often forgotten when people talk about interstellar travel is that they assume humans can simply step onto a ship and live in space for long periods of time. But our biology is not designed for that, because the human body evolved under the stable gravity conditions of Earth for millions of years. And when you remove that gravity, every system begins to change in ways you cannot ignore. Experiments on the International Space Station over the past few decades have provided very clear data. When astronauts live in a microgravity environment for just a few months, they begin to lose bone density at a rate of about 1% per month, equivalent to the rate of severe osteoporosis on Earth. And that is not just a number. It means that after a year, your bones weaken significantly, increasing the risk of fractures and making recovery difficult. At the same time, your muscles also weaken rapidly because they no longer have to fight against gravity, making it difficult to stand, walk, or perform normal activities when returning to a gravity environment. The cardiovascular system is also affected as fluids in the body redistribute, altering blood pressure and heart function, while the immune system becomes less effective, making the body more susceptible to infections in a closed environment. Even vision can be altered due to increased intracranial pressure in microgravity conditions, showing that no system in the body is unaffected. And if you think we can compensate for all of that with technology, then you face an even greater danger: cosmic radiation. Because outside the protection of Earth's magnetic field, astronauts are exposed to high-energy cosmic rays and charged particles from the sun, things that can penetrate materials and cause direct damage to DNA, leading to cancer, mutations, and long-term neurological problems. In missions on the ISS, radiation levels are already much higher than on the ground, and that is still in low Earth orbit, where there is partial protection. In deep space, especially during an interstellar journey lasting dozens or hundreds of years, this exposure can accumulate to extremely dangerous levels. This means you do not just need a ship, you need a complete artificial ecosystem that can operate stably for extremely long periods, providing oxygen, water, food, temperature control, pressure control, waste removal, and recycling everything almost perfectly, because there is no opportunity for resupply or repairs from outside. And any small error in such a complex system, if it occurs after 50 years, 100 years, or 200 years, can lead to irreversible consequences. You are demanding a system that not only works well, but must work almost perfectly for a time longer than any system humans have ever built. And this brings us to a very clear but hard to accept conclusion. The problem is not just putting humans on the ship, but keeping humans alive in a completely alien environment for an extremely long time. And that is a challenge for which we currently have no reliable solutions. When you put all these factors together, from bone loss, muscle weakening, changes in the immune system, effects on the brain and vision, to cosmic radiation, and the requirement for a perfectly operating life support system over decades or centuries, you begin to realize that biology is not a minor detail that can be solved later, but one of the greatest barriers. Because even if you solve the problems of speed, energy, and engineering, the human body itself may be the factor that makes the entire interstellar journey impossible in practice. There is an idea you often see in science fiction when facing the problems of time and biology. Instead of trying to keep humans alive and conscious throughout a journey lasting dozens or hundreds of years, you simply turn them off, freeze them, and wake them up when they arrive. A solution that sounds neat and almost perfect in theory. This idea is often called cryosleep, or cryogenic suspension, and it is based on the assumption that you can slow down or completely stop biological processes without causing damage, then restart them when needed. In reality, science has made some progress in this field, but those advances are mostly limited to very simple organisms, such as bacteria, some species of insects, or, in special cases, small biological tissues preserved at low temperatures. Even in modern medicine, freezing and thawing complex cells or tissues remains a major challenge, because when the water in cells freezes, it forms ice crystals that can rupture cell membranes and damage internal structures. For the human body, and especially the brain, the problem is far more serious, because the brain is not just a collection of cells, but an extremely complex network of neural connections, where memories, consciousness, and personal identity are stored in the physical structure of these links. If the freezing process alters or destroys those microscopic structures, then even if you can revive the body, you may not be able to restore the original person. Some methods, such as vitrification, turning the liquid into a glass-like state to avoid ice crystal formation, have been studied and applied in certain cases, but applying them to an entire human body, especially the brain, is still very far off. And even if you assume that successful freezing without major damage is possible, you still face another equally difficult problem: how to safely and completely reverse the process. Because thawing is not just warming up, it requires extremely precise control to avoid thermal shock, tissue damage, and unwanted chemical reactions. Up to the present time, there is no technology that can guarantee a human can be frozen for a long period and then fully restored with intact biological and cognitive function. This means that cryosleep, no matter how appealing in the imagination, remains only an unproven hypothesis in reality. And when you place it in the context of interstellar travel, where even the smallest error can lead to the failure of the entire mission, relying on an unproven technology becomes a risk that few civilizations would be willing to accept. So instead of being a clear solution, cryosleep is currently just a temporary way to avoid the problem, an idea that shows we recognize the difficulty of the equation, but we do not yet have a real answer for it. When you look at all the biological limits just mentioned, it almost becomes the only reasonable choice. Instead of trying to send humans along, you completely remove the biological element from the equation and let machines carry out the mission. Because robots do not have bones to lose density, they do not have muscles to weaken, they do not need oxygen, water, or food, and they are not affected by radiation in the way living organisms are. This immediately solves a whole series of problems we just discussed, from maintaining pressure, temperature, and gas circulation, to protecting DNA from high-energy cosmic rays. All the things you would have to build an extremely complex ecosystem for if you wanted to keep humans alive in space. When you switch to machines, you do not need life, you only need function. You only need a system that can operate stably, withstand harsh environments, and perform its task for a long time. And this is no longer theory, because we already have real examples like the Voyager probes, which have been operating for more than 45 years and are still sending data from the edge of the solar system. A clear demonstration that unmanned systems can exist and function far longer than any human could endure. If you expand this idea, you can imagine much more advanced robot ships equipped with artificial intelligence, powerful enough to navigate on their own, self-repair, and make decisions in situations where there is no intervention from Earth, especially when signal delays can last for years. Unlike humans, AI is not limited by biological lifespan. It does not age in the way we understand. And if its hardware is designed to be durable enough or capable of replacing parts, it can continue operating for hundreds or even thousands of years. This completely changes the way you look at the interstellar travel problem, because you no longer have to carry the full burden of life. You only need to carry a system that can observe, analyze, and transmit information. However, even in this scenario, things are still not as simple as you think, because robots do not automatically solve the other problems we have discussed, such as energy, collisions with interstellar dust, or the rocket equation. They only remove one layer of difficulty, but do not break the overall structure of the problem. Moreover, for a machine system to operate for thousands of years, you must solve another problem of durability and reliability, because every component has a lifespan, and every material degrades over time, especially in the high radiation and extreme temperature environment of space. That means you need systems capable of self-repair or self-replacement, a form of technology we have only just begun to touch at a very basic level. And if you want that system to be truly autonomous, you need an artificial intelligence flexible enough to handle situations that were never pre-programmed, which opens up entirely new questions about control, goals, and behavior of such systems over extremely long periods. But even with all those challenges, robots are still a far more practical choice than sending humans, because at least they are not bound by unchangeable biological limits. And this is the important point. If any civilization in the universe tries to cross the distances between the stars, it is highly likely they will not send living beings as we imagine, but will instead send machines, representatives without emotions, without biological needs, only with a mission. This also changes the way you think about the original question, because if something arrives from another star system, it may not be aliens in the traditional sense, but an automated system, a probe, a form of artificial intelligence sent on behalf of that civilization. And when you look at the overall picture, robots are not a perfect solution, but they are the only reasonable step forward in a problem where every other path seems blocked by the laws of physics and biology themselves. Going further than the idea of sending a single robot, you will almost certainly reach a much more powerful concept: self-replicating probes, commonly known as von Neumann probes after John von Neumann. And what makes this idea special is not the specific technology, but its logic. Instead of sending thousands or millions of ships from the start, you only need to send a single system capable of self-replication. When it reaches a new star system, it uses the resources there to create multiple copies of itself, and then those copies continue to spread to other star systems, repeating the same process. This turns the problem from linear to exponential, because the number of probes does not increase steadily, but grows exponentially with each generation. And with just a sufficiently stable replication rate, you would have a network spreading at an astonishing speed across the scale of the galaxy. Imagine each probe takes about 500 years to reach a nearby star system, exploit resources, and create 2 or 3 new copies, a number that is not unrealistic when compared to the distances between stars and the assumed technology. After a few thousand years, you would have dozens or hundreds of probes. After a few tens of thousands of years, that number would grow to millions. And after a few million years, the entire Milky Way could be filled by this network of devices. And here is the important point. A few million years may sound very long to you, but when placed next to the age of the galaxy, about 13 billion years, it is actually a very short period, occupying less than 0.1% of its history. This means that if even a single civilization in the entire galaxy had ever developed this technology, even just once in billions of years, then their probes should have spread everywhere long before Earth formed, let alone before humans appeared. And if that were true, you would expect to see traces of them everywhere, in the solar system, in asteroids, in unusual radio signals, or at least in astronomical observations. But in reality, we see nothing clear. There is no solid evidence for the existence of such a network. This makes the problem much more profound, because you have just removed one of the greatest obstacles, biology, and you have significantly reduced the energy requirement for each mission. Yet the paradox remains, and this is exactly where things become intellectually uncomfortable, because if a solution that seems reasonable, efficient, and almost optimal, like this, still does not appear in the data, you are forced to consider that there may be other limits we do not yet understand, perhaps concerning the stability of self-replicating systems, perhaps the unintended risks of allowing a system to reproduce freely, or perhaps civilizations are smart enough to recognize those dangers and deliberately avoid them. You can also consider the possibility that the probes exist but are not easy to detect. They may operate in ways that do not draw attention, or in areas we have not observed carefully enough. But even if you accept those possibilities, the basic problem does not disappear, because the scale and time involved are so large that the absence of evidence becomes meaningful. And this brings you back to the original question, but at a deeper and more uncomfortable level. Not just why aren't they here, but why don't even their most efficient representatives appear clearly? And when you cannot answer that question with simple assumptions, you begin to realize that there may be systemic barriers, limits that lie not only in basic physics, but also in the way complex systems operate over very long periods. So instead of resolving the paradox, the idea of von Neumann probes actually makes it sharper, because it removes one easy layer of explanation and forces you to confront the possibility that the universe is not only physically difficult to reach, but also has deeper dynamics that prevent even the most rational strategies from being carried out, or from leaving traces we can recognize. At this point, after having gone through all the most reasonable possibilities, from sending humans to switching to robots, and then to self-replicating systems like von Neumann probes, you almost have no choice but to return to the original question that Enrico Fermi posed in 1950. But this time it is no longer a simple question. It has become a problem that carries the full weight of physics, of the numbers, and of the limits we have just gone through. You can no longer easily say maybe they just haven't arrived yet, because you have seen how truly difficult arriving really is. You have seen the distances, energy, time, biology, and even the alternative solutions like robots and self-replicating probes all have their own problems. And what is remarkable is that even after you have removed each of those layers of difficulty, you still stand before the same reality. We see nothing. There are no alien spacecraft in the solar system, no clearly confirmed radio signals from extraterrestrial intelligence, no massive structures like Dyson spheres definitively observed in astronomical data, and no clear signs of a self-replicating probe network that has spread across the galaxy. This does not make the problem smaller, it makes it larger, because now you are not only asking why aren't they here, but also why is there no trace of any effort to come here? And when you think about it carefully, you begin to realize that this silence is not a random detail, but a fact that needs to be explained, a fact that any theory about life in the universe must account for. You can try following familiar directions. Perhaps intelligent life is rarer than we think. Perhaps civilizations self-destruct before reaching the interstellar stage. Perhaps they are not interested in exploration, or perhaps they exist in ways we have not yet recognized. But each such hypothesis must face the same reality, that we have no direct evidence. And this is where the question becomes a bit more personal, because you have to ask yourself what you really expect. Do you expect a ship to appear in the sky, a clear signal, an unmistakable sign, or just a small anomaly in the data that we can interpret in many ways? Because the way you define evidence will affect how you view this silence. But even if you expand that definition, you still have to face the reality that we have not seen anything convincing enough to conclude that someone has overcome the barriers we just analyzed. And that leads to a very intellectually uncomfortable state, where you cannot easily dismiss the possibility of extraterrestrial life, but you also cannot easily explain why we see no traces of it. This is the essence of the paradox, not the lack of answers, but having too many possibilities with none of them confirmed. And when you stand at this point, you begin to understand that perhaps the problem is not that we have not looked in the right place, but that we are asking the wrong question. Instead of asking where are they, perhaps the question should be what prevents them from appearing in the way we expect. And when you frame the question that way, you begin to prepare for a conclusion that no longer relies on hope or imagination, but on what physics allows and does not allow. Because if all the paths to visiting are blocked by the limits we have seen, then the silence of the universe may not be a mystery to be solved, but a natural consequence of the way the universe is built. If you are not satisfied with all the limits just mentioned, you will almost certainly turn to an idea that sounds like the final escape, space tunnels or wormholes, a concept that originated from the Einstein-Rosen bridge proposed by Albert Einstein and Nathan Rosen in 1935, in which two very distant points in space can be connected by a shortcut through the structure of space-time. Mathematically, this idea is entirely valid within the equations of general relativity, and if you could create a stable wormhole, you could travel between 2 points thousands of light years apart in a very short time without having to cross the distance in the conventional way. This sounds like the perfect solution for all the problems we have discussed, because it bypasses distance, does not require accelerating to extremely high speeds, and is not directly limited by the speed of light in the traditional sense. But this is where things start to become complicated, because the wormhole solutions we know have a very important feature. They are not stable. That means if you try to use them, they will collapse almost immediately before anything can pass through. To keep a wormhole open, you need a very special form of matter with negative energy, something with negative energy density that creates pressure opposite to ordinary matter, a thing we have never observed at the required scale. In quantum physics, there are effects like the Casimir effect that suggest negative energy can exist under very specific conditions, but these effects are extremely small and cannot be scaled up to astronomical sizes to keep a wormhole large enough for a ship to pass through. This means that although wormholes exist as a mathematical possibility, turning them into a practical tool requires conditions we do not know how to achieve, and it is not even certain whether they can exist stably in the real universe. In addition, even if you assume that an extremely advanced civilization could create or find a natural wormhole, they would still face other problems, such as controlling the entry and exit points, ensuring stability during travel, and dealing with quantum effects that are not fully understood. And most importantly, up to the present time, we have no observational evidence that wormholes exist in the universe. No signals, no structures that can be confirmed as a space-time tunnel. So although this idea is very appealing and is often used as an escape in the imagination, it still lies entirely within the realm of theory. And when you return to the original question, it does not really solve the problem, but only postpones it, because you are replacing one set of barriers with another set that is even harder to understand. And that brings you back to the same point. If other civilizations are relying on technologies like this to travel between the stars, we should still see some traces of them, but we do not. And this once again reinforces the idea that solutions we imagine, even if mathematically reasonable, may not exist or may not be feasible in the physical reality of the universe. If wormholes still sound too science fiction, but you are not ready to give up the idea of traveling faster than the usual limits, then you will almost certainly encounter another proposal that appears in modern theoretical physics, the so-called warp drive, specifically the Alcubierre drive model proposed by physicist Miguel Alcubierre. The special thing about this idea is that it does not try to push the ship beyond the speed of light in the traditional sense, but instead tries to bend space itself around the ship. In theory, you can compress space in front and expand space behind, creating a bubble in which the ship is almost stationary, but the entire bubble moves through space faster than light relative to the outside. This allows you to go from point A to point B in a very short time without directly violating the local speed of light limit. It sounds like a perfect escape from all the barriers we have discussed, because you do not need to accelerate to extremely high velocities. You do not face time dilation in the usual way, and you are not bound by the rocket equation. But just like wormholes, the problem lies in moving from mathematical equations to physical reality, because to create such a warp bubble, you need a very special form of energy, often called negative energy or exotic matter, something with negative energy density that we have never observed at the required scale. Initial calculations showed that the energy required could be equivalent to the mass of an entire large planet, like Jupiter, and in some models even much larger, a number far beyond the capability of any civilization we can imagine based on current knowledge. Although later theoretical improvements reduced the energy requirement, it still remains at an extremely large level and demands forms of matter that we do not know how to create or control. In addition, there are other problems such as the stability of the warp bubble, how to start and stop it, as well as possible side effects on the surrounding environment when space is distorted at such a large scale. And once again, the most important thing is that we have no experimental evidence that this technology can exist outside the equations, no experiments proving that we can create or control the necessary conditions to make it work. So even though warp drive is an extremely appealing idea and is often seen as a final escape in the imagination, it remains only an unverified theoretical model. And when you place it in the context of the original question, it does not really solve the paradox, but only pushes it to another level. Because if advanced civilizations actually use technologies like this, we should still see traces of them somewhere, but we do not. And this once again brings you back to the same uncomfortable conclusion that solutions that sound reasonable in theory may not exist or may not be feasible in the real universe we live in. After having gone through each idea that humans have ever hoped could open the door between the stars, you begin to see a unified picture gradually emerge, not as scattered hypotheses, but as a tightly linked chain of logic, where each barrier does not stand alone, but reinforces the others. The distances in the universe are not just large, but large enough to break intuition, with numbers like trillions of kilometers for each light year and tens of thousands of light years for the scale of the galaxy, making any journey last far beyond the time frame of a single civilization. The speed of light is not just fast, but an absolute limit encoded into the structure of space-time, where no object with mass can reach it, no matter how advanced the technology becomes. And this is not a technical problem, but a mathematical result from Albert Einstein's equations. The energy required to approach speeds near light is not just large, but increases in a way that quickly exceeds any realistic capability, with numbers on the scale of the total energy a civilization consumes over a long period, and that is only for acceleration, not counting deceleration, return, or maintaining the system. The rocket equation that Konstantin Tsiolkovsky proposed shows that each step of acceleration brings an exponential increase in fuel mass, making ship design quickly become unrealistic when you push it to interstellar scales. Even if you imagine alternative solutions like robots or artificial intelligence, you only solve part of the equation, because the problems of energy, collisions with interstellar dust, and system durability still remain. Stronger ideas like von Neumann-style self-replicating probes could theoretically spread across the galaxy in a few million years, a very short time compared to the age of the universe, but in reality we see no traces of them, which raises deeper questions about the feasibility or desirability of such systems. When you turn to theoretical escapes, like wormholes or warp drive, you encounter other barriers, from the instability of wormholes to the requirement for negative energy and exotic matter for which we have no evidence of existence at the required scale. All the paths you try lead to the same result, not difficult, but possible, but blocked by the very structure of the laws of physics. And this is the most important point to understand, because when you talk about technology, you are talking about things that can change over time, things that can be improved, optimized, and developed. But when you talk about the laws of physics, you are talking about fundamental limits, things that do not depend on the intelligence or level of progress of a civilization. Any civilization that exists in this universe, whether they are millions or billions of years ahead of us, must obey the same set of rules, the same limits on speed, energy, and space-time structure. This means the problem is not we are not advanced enough to reach the stars, but reaching the stars in the way we imagine may not lie within what the universe permits. And when you look back at Enrico Fermi's original question, you begin to see that perhaps we have been looking for the answer in the wrong place. We searched in engines, in technology, in the will to explore, while the answer may have been in the equations from the beginning. It is not that they do not want to come. It is not that they do not exist, but that they may not be able to come, at least not in the way we imagine visiting. And this is not a pessimistic conclusion, but one that is consistent with everything we have analyzed. Because when you put all the barriers together, the enormous distances, the speed of light limit, the nearly impossible energy requirements, the biological problems, the collision risks, and the uncertainty of theoretical solutions, you no longer see any clear path leading to a civilization being able to move freely between star systems. This makes the simplest answer, in the true spirit of science, the most reliable one. Not a conspiracy, not a cover-up, not a strange coincidence, but a natural consequence of the laws of physics, that civilizations, if they exist, are isolated by the very structure of the universe. And when you accept that, the silence of the night sky is no longer a mystery that needs to be explained with complex hypotheses, but becomes a sign, an indirect signal that the universe is not designed for easy travel between the stars, but is structured in a way that keeps every civilization, no matter how intelligent, confined to its own small region. And that may be the simplest and clearest solution to the paradox we started with. The physical barriers may be enough to prevent travel between the stars in the way we imagine. There is another idea that appears as an additional layer of explanation, not replacing but stacking on top of what we have seen. The great filter, a concept that suggests that in the sequence of development from inorganic matter to life, from simple life to intelligence, and from intelligence to an interstellar civilization, there exists one or more extremely difficult filters to overcome, to the point that most star systems never complete that path. The important thing here is that the great filter does not necessarily lie at a single point. It could be at a very early stage, such as the formation of life from chemistry, or at a later stage, such as the ability to maintain a technological civilization long enough to expand beyond the planet. And when you combine this idea with all the physical barriers we have discussed, you begin to see an even more complex picture, where not only going out is difficult, but surviving long enough to even try it is already a challenge. One of the worrying possibilities is that civilizations tend to self-destruct before reaching a high enough level, not because they are stupid, but because their own technology creates new risks that they cannot control in time. You can look at our own recent history to see this. With nuclear weapons appearing in the mid-20th century, for the first time in human history, we gained the ability to completely destroy our own civilization in a very short time, and to this day that danger has not completely disappeared. Alongside that is climate change, a consequence of industrial activity that we are gradually realizing could alter the entire living conditions on the planet, not immediately, but enough to cause major disruptions over centuries. And these are just two examples in a longer list, where each technological step not only opens opportunities, but also creates new dangers, points where, if mishandled, could lead to collapse. When you add the rapid development of artificial intelligence, you get another layer of risk, not just a tool, but a system that could become autonomous, with goals that do not fully align with human interests. And if not controlled, it could create consequences we cannot yet predict. This leads to a very uncomfortable question. Not can we develop technology powerful enough to travel between the stars, but can we survive long enough to reach that point? And this is exactly where the great filter becomes important. Because if the filter lies ahead of us, if most civilizations reach a certain level of technology and then self-destruct, or are destroyed by the very systems they created, then the fact that we do not see anyone in the universe is no longer surprising. It becomes the natural result of a process where very few systems make it through all the stages. But there is also another possibility, that the great filter lies behind us, that the formation of complex life or intelligence has already been extremely rare, and we may be one of the few cases that have overcome the hardest steps. If that is true, then the silence of the universe is not a sign of danger ahead, but a sign of rarity behind. The problem is that we do not know where the answer lies, and that very uncertainty makes the question more profound, because if the filter lies ahead, then our future is not about expanding to the stars, but about surviving the risks right here on this planet. And when you look at all these factors together, you begin to see that the Fermi paradox is not just a question about aliens, but a question about ourselves, about the long-term survival of a technological civilization. It forces you to look at what we are doing, the decisions we make, and how we manage the power we are gradually acquiring. Because perhaps the answer to the silence of the universe does not lie in the distances between the stars, but in the gap between technological capability and the control capability of a civilization. And that is why, when you ask whether we have passed the great filter or not, the most honest answer is that we do not know. And perhaps we are right in the middle of that process, where every step not only determines our future, but also determines whether we will ever become one of the civilizations that can survive long enough to even set foot outside our own star system. Going through the entire chain of arguments from distance, speed, energy, biology, technology, and even hypotheses like the great filter, you begin to realize that the answer does not lie in any single detail, but in the way all those factors combine with one another. And what this overall picture shows is not that the universe is preventing us in any active sense. There is no force trying to hold us back, no rule designed to isolate civilizations. It is simply that the laws of physics set limits that any system existing in this universe must obey. The speed of light is not a barrier erected to obstruct us. It is merely a property of space-time. Energy does not become enormous because the universe wants to make things difficult for us, but because that is how kinetic energy works at high velocities. Biology does not become fragile in space for any special reason, but because it evolved in a completely different environment. And when you look at everything that way, you begin to see that what we call barriers are actually just natural consequences of the way the universe is structured. This has a very important consequence. These limits do not apply only to us, but to every other civilization, no matter where they are, how advanced they are, or how long they have existed. If they are built from the same matter, exist in the same space-time, and obey the same laws of physics, then they must also face the same problems we are seeing. You can imagine a civilization millions of years ahead of us, but they do not have a different version of the universe to operate in. They cannot choose a more favorable set of physical laws. They are still bound by the same equations we are using. This leads to a conclusion that may initially feel uncomfortable, but is extremely consistent. The isolation between civilizations may not be an accident, but an inevitable consequence, a direct result of physical limits combining in a way that makes travel between the stars nearly impossible to carry out in practice. And when you ask the question, are we alone? The answer may not be a simple yes or no, because the universe is too large for you to claim that we are unique. But at the same time, the very limits we have analyzed also show that even if other civilizations exist, they may be separated from us in a way that we cannot overcome. We may not be alone in terms of existence, but we are alone in terms of experience, alone in our ability to interact, confined to a small region of the galaxy that we call home. And this completely changes the way you look at the night sky, because instead of seeing an empty space that needs to be filled with stories or hypotheses, you begin to see a structure where silence is to be expected, where distance is not just space, but a kind of wall created by the laws of physics themselves. And when you understand that, Enrico Fermi's question is no longer a paradox that needs to be solved with increasingly complex assumptions, but becomes a reminder that sometimes the simplest answer is the correct one. It is not that they are hiding, not that they are watching us, but that they may also be looking up at their own sky and asking the same question. And this is where the way you perceive your place in the universe begins to change. Because if isolation is real, if civilizations are confined to their own islands in the ocean of space-time, then the value of what we have here becomes much greater. Every step forward, every decision, every way we use technology not only affects the near future, but may determine whether we survive long enough to understand more about the universe.